In the previous lesson, we learned how to estimate limits by using graphs and tables of values, and those methods helped us understand what happens to a function as x gets closer and closer to a particular value, and it also helped us make that educated guess on what we thought the limit was. Now, in this lesson, we're going to learn a faster and more efficient way to evaluate limits. Instead of using graphs or tables every time, we're going to use a set of rules called the limit laws. And the limit laws allow us to evaluate a lot of different limits using algebra. So you're going to have to go back into your brain from algebra class and probably sometimes from trig class and pull out those skills like factoring, complete the square, using conjugates, and those kinds of tricks that we can use to apply along with these limit laws. Now, the limit laws allow us to evaluate a lot of limits using algebra, and once you learn these rules, you'll be able to solve a lot of limit problems by simply applying the appropriate limit law. So let's look at two important results that we covered in the previous lesson, but I didn't officially define it. So in this lesson, we're going to officially define it. We have the first rule that the limit as x approaches a of the function x is equal to a. If we think about the function y is equal to x, it's just this linear function that passes through the origin. Now, no matter what value of x I approach, we'll call it a here because that's how it's labeled in the rule up here in number 1. We're going to just generically call it a. So when I approach a from the left or from the right, because this is the graph y is equal to x, every point on this graph is going to have the same value for x and y. So as I get closer and closer to a as my x value, I'm going to be getting closer and closer to a as my y value. So the limit as x approaches a of our function x is going to be a. Now, that was for rule number 1. For rule number 2, we have the limit as x approaches some value a of the constant function c, and that's going to be c. So if we look at our constant function, y is equal to c, so it could be 5, it could be 7, whatever that constant value is for c. As I approach my value of a from either direction, from the left or from the right, and I come up and I look to see what I'm getting closer to for my y value, because all the y values on that constant function is going to be c, my limit is also going to be c. So that's why we have that second rule. So looking at this, this is called the identity function, although I didn't call it that before. That's because no matter what I plug in for x, y is going to be the same thing. All right, now, as x gets closer and closer to 2, remember, x is just this function that passes through the origin. Y is equal to x, and in this case, we're approaching positive 2. So as x approaches 2 from either direction, I'm getting closer and closer to the y value of 2. So my limit as x approaches 2 for the function x is going to be 2. Now, looking at part B, this is a constant function, and no matter what value of x we choose on the function, the value for y is always going to be 5. So here's my x and y axis. Here's my sketch of the graph. Y is equal to 5. So as I approach 2 from either direction, for my x value, my y value is going to be 5 because every value of y on that line is 5. So the limit as x approaches 2 of the constant function 5 is equal to 5. So now that we looked at what we need to understand in order to get through these limit laws, let's take a look at these limit laws here. So let's first understand what all of these letters and symbols and everything mean. So f of x and g of x are functions, and they're going to be defined for all x not equal to a on some open interval that contains a. So in other words, we're not going to make the assumption that the function is defined at a when we're trying to approach a. But everything close to it will be defined. The letters L and M are going to be the limits for f of x and g of x respectively. So L is going to be the limit for f of x and M is going to be the limit for g of x. So we're making the assumption that we know what those limits are. Now, when we look at the first rule, it's called the sum law for limits. Now, the sum law tells us that the limit of the sum is the same thing as the sum of the limits. If I create a new function by adding f and g together, and I take the limit as x approaches a, since I know that the limit for f of x and g of x exists at that point a, and I know what their values are, I know that they're L and M, then I can take the limits separately and just add them up. So I find the limit of f of x, I find the limit of g of x, which I know what they are, and I add them up. The difference law for limits works the same way. To find the limit of one function minus another, we just find the limit of each first and then subtract. So here's our new function that we created by finding f of x minus g of x. And since we know those limits exist individually, I can find the limits individually and just subtract L minus M. The constant multiple law for limits, that says that if a function is multiplied by a constant, so I know what the limit is for f of x as x approaches a, but let's say I have a 3 in front of it. I'm multiplying 3 by the function. Okay, then we can leave the constant alone and pull it on the outside, find the limit, and then multiply that constant by whatever the limit is. So I can take this c out in front and find the limit of f of x, because I know that limit is L because we were told that in the beginning, and then take c and multiply it by L. Okay, so similarly, for the product law, and I know that those limits individually exist, I can separate them, find the limits separately, and then multiply the limits together. The quotient rule again works the same way. If I create a new function by taking f of x divided by g of x, and I know individually what those limits are, I can find the limits individually and then divide. So I know that the limit of f of x is L, I know that the limit of g of x is M, and I just divide this. But this is assuming that the limit for g of x is not equal to 0, because remember, we can't divide by 0. So that's the only thing that we have to be careful with there. Okay, the power rule says that powers and limits work well together as well. We can find the limit first and then raise that answer, whatever our limit is, to the power. Okay, and then the root law is the same idea, where we can find and move the roots on the outside of the limit, find the limit first, and then take the square root. And it doesn't have to be the square root. It could be the cubed root or any other root. We just have to make sure that if it's an even root, that we don't have a negative under the even root. So let's look at this example. We're going to apply the limit laws to the limit as x approaches negative 3 of the function 4x plus 2. I want you to think of the 4x as one function named f of x, and the 2 is a constant function g of x, and I'm adding them together. So we can use the sum law to separate this into two limits. I can rewrite this as the limit as x approaches negative 3 of f of x, which is 4x, and then add the limit as x approaches negative 3 of g of x, which is 2. And then I can use the constant rule where this 4 can come out in front. So I can do 4 times the limit as x approaches negative 3 of x plus the limit as x approaches negative 3 of 2. And now we have it based on those two very basic rules that we talked about at the beginning. I have 4 times, now I know that the limit of x as x approaches negative 3 is just negative 3. And the 2, that's a constant function. So no matter what value of x I'm approaching, I know my limit is going to be 2. So now I just have to work out this arithmetic, and I get negative 12 plus 2, and that gives me a negative 10. So if I looked at this on the graph, if I graph 4x plus 2 and I look at as x approaches negative 3 from either side, I'll see that I'm getting closer and closer to the y value of negative 10. So you can see these limit laws actually allow us to just use direct substitution. If I don't run into any problems where I have a negative under a square root or a 0 in the denominator, I can just directly plug in what I'm approaching. So it might seem like this is a lot of writing for just plugging in, but I'm trying to break down how these limit laws are used. Once we get through this lesson and we get through a few examples, I would be completely okay with you showing me this. Four times negative 3 plus 2 is equal to negative 10. All right, let's do one more example. Whenever you're working with a function that has a denominator or a root or something where we're concerned about getting something undefined, like 0 in the denominator or a negative under an even root, we want to check first, if I plug 2 into x, am I going to run into a problem of getting 0 in the denominator? In this case, we don't. So I can use the limit laws here and use direct substitution to just plug in and find out what my value of y is. But there are tricks that we're going to use coming up of how to handle it if we do have 0 in the denominator. So I'm going to break this entire rational function down. So I'm going to be using all the limit laws. So first I'm going to use the quotient rule, and I'm going to divide the limit as x approaches 2 of the function 2x squared minus 3x plus 1, and I'm going to divide that by the limit as x approaches 2 of the function x to the third plus 4. So here I just use the quotient rule because I know that if I plug in 2 in the numerator and the denominator separately, I'm not going to run into any issues. So I can use the quotient rule and just take the limits separately and then divide. So I'm now going to break up the numerator. I can take the limit as x approaches 2 of 2x squared. Now I'm going to use the difference rule to subtract. So now I have the limit as x approaches 2 of 3x. Then now I'm going to use the sum rule where I'm going to add the limit as x approaches 2 of the constant function 1. Now down below I have the limit as x approaches 2 of x to the third. Using the sum rule, I can then add the limit as x approaches 2 of the constant function. Now this is where I can break it down even more using the power rule and the constant rule, where I can bring a constant in front. So lastly, I'm going to take this 2 and bring it out front. I'm going to take this 3 and bring it out front. And then I can also square the limit after I separate it. So I'm going to have 2 times the limit as x approaches 2 of x, and then I'm going to square the limit. Now, minus, I can bring the 3 out in front and say 3 times the limit as x approaches 2 of x, plus the limit as x approaches 2 of 1. And then I'm going to do the same thing down here. I'm going to use this cube, and I'm going to use the power rule to find the limit first and then cube it. So I'm going to take the limit as x approaches 2 of x and cube it, and then add the limit as x approaches 2 of 4. So what we have now is we've broken the limits all down to where we have the limit of x or the limit of a constant. And then we can just use direct substitution. So if I find the limit as x approaches 2 of x, looking at the numerator, that's going to be 2, and then I can square 2, which is 4, and then I have the 4 times the 2 that's in front, that gives me 8. All right, then I'm going to subtract, when I plug 2 in for x, the limit as x approaches 2 of the linear function x, I get 2, and then I get 2 times 3, which is 6. And then the limit of a constant function is just the constant itself. Now in the denominator, I have the limit as x approaches 2 of x. So I would plug 2 in and I would get 2. And then 2 to the third would give me 8. Plus, and then I have the limit of a constant, which is just the constant. So my final answer is going to be 3. When I combine the top, 8 minus 6 is 2, plus 1 is 3. And then on the bottom, I have 8 and 4, which is 12. And then I can reduce that to 1/4. So my limit, if I look at this function as a whole, if I graph it on my calculator, so as I get closer and closer to 2 from either direction, I'm going to be getting closer and closer to a y value of 1/4.